Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome to you all in massive open online course, and today I am starting module 3. First lecture I will be delivering today for the module 3. Let us see what are the topics that I intend to cover in this lecture. The topics that I intended to cover is Levy's method for rectangular plate, then general solution of the plate equation by Levy's method, symmetrical and antisymmetrical solutions, illustration of problem of rectangular plate carrying uniformly distributed load using Levy's method. So, you have understood that today our main focus is to analyze a rectangular plate using another method, whichever we learned earlier was the Navier's method. Now, we will use a rectangular plate using Levy's method. So, let me see what is the difference between these two methods. If we recall that Navier's method, then we used the double trigonometric series for the solution of the plate deflection. Now, this is possible only when all the edges of the plates are simply supported. So, in a rectangular plate 4 edges are simply supported, then we can handle the problem by Navier's method, which gives a very simple solution with double series. Of course, the double series increases the complexity in summation, but the series is rapidly convergent. Here we use another method, Levy's method, for the rectangular plate, but difference is that in Levy's method 2 opposite edges must be simply supported. So, Levy has proposed a solution considering 2 opposite edges to be simply supported, for which he proposed a closed form exact solution. Now, what about the other 2 edges? Other 2 edges may be simply supported also, or may have any other conditions. That means, other 2 edges may have one edge may be fixed, other edge may be free, or one edge may be simply supported, other edge may be supported on elastic beam. The Levy's method only is possible when 2 opposite edges are simply supported, but a plate when all edges are, say for example, is clamped, then directly using Levy's method or Navier's solution is not possible. We will discuss it later by using indirectly this Levy's method, how can we obtain the solution for a clamp plate. Okay. So, our intention is to discuss the Levy's method for rectangular plate, general solution we will formulate, and then symmetrical and antisymmetrical conditions, how it arises and what are the simplification possible in case of these two special conditions, and for general condition what we will do. So, that will be discussed. Then I want to illustrate a problem that we have already solved by Navier's method when the all edges of the plate was simply supported. So, this problem now I will solve it by Levy's method, and the plate that I consider in the last section here, that will be carrying a uniformly distributed load. Okay. So, Levy has shown that a single trigonometrical series can be used to represent the deflected surface of a rectangular plate, which satisfy simply supported boundary condition at 2 opposite edges. Now, consider this plate, that here these edges, say x is equal to 0 and x is equal to a, these edges are simply supported. The dotted line shows that it is simply supported. This symbol we generally use for simply supported condition. The other two edge y is equal to 0 and y is equal to b may have any other condition. So, I have not specified it. The condition will be imposed to evaluate the constants of integration, that we will see later on. So, you have seen that x is equal to 0 and x is equal to a, the plate is simply supported, and therefore, Levy proposed a solution w x y single summation a function of y, that is called capital Y m as a function of y sin m pi x by a. So, the sum is over with only one term. So, that means, when I expand the series, it will be say y 1 sin pi x by a plus y 2 sin 2 pi x by a plus y 3 sin 3 pi x by a, like that it will go. So, the function y m has to be evaluated, because this is still unknown, because we did not satisfy the boundary condition on other two edges, but these edges say x is equal to 0, x is equal to a, the boundary condition is satisfied by taking the sine function to represent the boundary condition at the two opposite edges, because immediately we can see that when x is equal to 0, the w is 0, and when x is equal to a, again the w is 0. So, in both the edges deflection is 0. So, when we consider the bending moment condition, that is the bending moment is given by minus d, then in multiplied by the curvature in x direction plus mu into curvature in y direction. So, since the plate is supported along the y direction, there will be no deflection along the y direction at the edge. So, therefore, curvature is 0 along this x edge, x is equal to 0 or x is equal to a edge. So, therefore, the boundary condition for bending moment only reduces to the curvature del square w del x square equal to 0. And we can readily see, you can verify that by taking this function w x y equal to y m into sin m pi x, the boundary condition is easily satisfied, all the boundary condition, geometric as well as this force boundary condition. Now, I think you have understood the difference between the Navier's method and Levy's method. Navier's method requires that all edges have to be simply supported. So, that means, here I left this edge y is equal to 0 and y is equal to b edge as unknown boundary conditions, but in Navier's method these boundaries are also have to be simply supported. So, this is the difference. So, the generality of the approach has been improved in case of Levy's method. Okay. So, taking a single trigonometrical series, we have seen that boundary condition is satisfied at x is equal to 0, x is equal to a, and other boundary condition y is equal to 0, y is equal to b is not specified yet, and depending on the different S condition we will be able to evaluate the unknown constants of the integration, that we will see later. Okay. Now, it is the plate equation, that equation number 2 is well known to you, del 4 w equal to q x y divided by d, where del 4 is the biharmonic operator, that is this partial derivative operator, that is del 4 by del x 4 plus 2 del 4 del x square del y square plus del 4 del y to the power 4. So, you know this operator, and this is operating on w, and on the right hand side q x y is the distributed load, that means q is a continuous function of x and y, but sometimes the discontinuity arises because the concentrated load may also act, and there are also the strip loading or line loading. So, in this case we have to deal with separately the Levy's method, and capital D is flexural rigidity of the plate. What is the flexural rigidity of the plate? Flexural rigidity of the plate is nothing but E h cube divided by 12 1 minus mu square, where E is the Young's modulus of elasticity, h is the thickness of the plate, and mu is the Poisson ratio. Now, one thing here can be noted, that while solving the differential equation we have taken the uniform thickness of the plate. So, therefore, d is not variable in x and y. So, that is the characteristics of this differential equation. When d is variable, then plate equation will be complicated and different techniques have to be used. Okay. Now, on expansion, the del 4 w looks like that, that is del 4 w by del x to the power 4 plus 2 del 4 w divided by del x square del y square plus del 4 w del y to the power 4 equal to q by d. So, you have understood that there are 3 terms, and right hand side this is the load function and flexural rigidity, and left hand side all are actually 4th order derivative. So, if we see the function w x y is equal to y m y sin m pi x is the proposed solution of the differential equation, because it satisfied the boundary condition on 2 opposite edges completely. So, if it is the solution, possible solution of the differential equation, then it must satisfy the differential equation also. So, substituting this series w x y equal to y m into sin m pi x by a into the differential equation, we get an equation like that. Say this is the first term, that is the after differentiation of w 4 times with respect to x, we get m to the power 4 pi to the power 4 a to the power 4 y m y, because capital Y m is a function of y. So, it remains undifferentiated, and then sin m pi x after even number of differentiation it appears as sin m pi x by a. Now, one thing is that the m is the half wave number. So, m can vary 1 to infinity, and for you have seen for different half wave number the waves are formed, and the superimposition of all waves actually contributes to the total deflection of the plate. Then del 4 w del y to the power 4. Now, here we are taking the differentiation with respect to y. So, therefore, this quantity has to be differentiated 4 times, but this is treated as a constant. So, it remains as it is. So, sin m pi x by a remains as it is, but this function is differentiated 4 times with respect to y. Okay. Then second derivative, this middle intermediate term or middle term is del to the power 4 w by del x square del y square. That means, second derivative of w with respect to x square is first taken, then second derivative of this result is again evaluated 2 times with respect to x, okay, or vice versa, because the operators are interchangeable. It is a linear operator. So, you can proceed in either way. So, after doing this operation, you will get here actually you will get the minus sign will come appear in this equation, and you will get m square pi square by a square d square. This is the second derivative of y m y dy square and sin m pi x by a. So, the minus sign appears here, and then substituting this derivative in this equation completely, we get this term, and it is under the summation term. So, it is under the summation term, and sin m pi x is there, and q x y by d. Now, our intention is to solve for this differential equation, but we have to get rid of this summation term. That means, there are 2 ways you apply here orthogonality condition to get rid of this summation term, or you can express q x y in terms of Fourier series, and then comparing the like terms you will get the coefficient. So, both are same and will give the same results. Now, here we have proceeded from the first working principle. So, multiplying both sides of the equation 3, that equation I am numbering it as 3, by sin m dash pi x by a, integrating with respect to dx in the limit 0 to a. So, why I have taken this sin m dash pi x by a, because m dash is also an integer. So, when sin m pi x by a is multiplied by with another sine function of m dash pi x by a when m and m dash are integers, and when it is integrated from 0 to a with respect to x, that value will be 0 if m is equal to not m dash. Means when we carry out summation, we will encounter here that sin say m is equal to 1 and m is equal to 2. So, we will get sin pi x by a, sin 2 pi x by a. So, it will be 0. Then we will get sin say 2 pi x by a, sin say here 2 pi x by a. So, it will be m and m dash are equal. So, it will not be 0. So, according to orthogonality condition, that sin m pi x by a, sin m dash pi x by a dx equal to a by 2 if m is equal to m dash. But for other value of m, this is never the non-zero value. When m is equal to m dash, it will be a by 2. When m is equal to not m dash, then this integral will be reduced to 0. Okay. So, equation 4 now can be written, because after integration only one term will remain and it will be a by 2. So, this is written as like that, because a by 2 will now transfer to the right hand side. So, it will be here, it will be 2 a divided by a d, and this term will remain as it is. So, naturally we get here this is the ordinary differential equation, because only one function, that is y m, which is a function of y, is differentiated. So, capital Y is a function of y. So, it is fourth derivative appears here, then here it is second derivative, and here the function itself. So, right hand side you are getting 2 a d integration 0 to a q x y is the distributed load on the plate. This may be any form, it may be uniformly distributed load, it may be partially distributed load, it may be say hydrostatic load, that is uniformly varying in a linear manner, or it may be a load which is non-linearly varying. Any type of variation of load may be there in practical cases, and this is the general term for evaluating the load function that can be easily incorporated when q x y have continuous distribution. So, here you can see that right hand side now becomes a function of y, because the integration is carried out with respect to x. Clear? So, integration is carried out with respect to x, and it is a definite integral. So, the x variable will be replaced by the constant term which is a, the limit of the integration. So, therefore, there will be no x variable in the integration result, and it will be simply a function of y. So, this differential equation turns out to be d to the power 4 y m y divided by dy to the power 4 minus 2 m square pi square by a square d square y m y divided by dy square plus m to the power 4 pi to the power 4 divided by a to the power 4 y m y, and this is the function of y equal to f m y. So, this differential equation we need to solve completely, so that we know the function y, capital Y, and then the full deflected surface is known. Because now at this moment we are only knowing this function sin m pi x by a, but still this function y m y is remaining unknown till now. So, let us see how we can solve it. So, this function of y, as I have explained, that it is integrated with respect to x and the limit is substituted, and then you will get a function where x variable does not appear. Okay. The equation 6, you can see this equation is a ordinary fourth order differential equation with constant coefficient, linear differential equation with constant coefficient, but this equation is non-homogeneous because of the presence of the forcing function, which is appearing as a function of y. Okay. So, because of this non-homogeneous equation, as per the theory of linear differential equation, we have to find the solution in two parts. One is homogeneous solution and second is particular integral or particular solution. Homogeneous solution is obtained when there is no load function, that is right hand side is 0, and particular integral has to be obtained when the right hand side represents the forcing function, whatever force may be. Okay. So, equation 6 has to be solved, first homogeneous part and particular integral, then we will superimpose one over other, because it is a linear differential equation. So, complete solutions will be obtained. Now, you can see here it is a fourth order differential equation. So, naturally in fourth order differential equation, when you get the complete solution of homogeneous equation, we get 4 constants of integration. That 4 constants have to be evaluated using the boundary condition at the 2 other opposite edges. We have not touched the boundary condition, or we have not spelled out any boundary condition on other 2 edges. In Levy's condition, when we started the formulation, we stated that the 2 edges x is equal to 0 and x is equal to a are simply supported. So, 2 opposite edges, other 2 opposite edges y is equal to 0, y is equal to b, the boundary condition is still now not specified. Okay. To solve the homogeneous part of the equation, we will consider the right hand side to be 0. So, right hand side is considered to be 0. Okay. So, now using the theory of linear differential equation, we assume that solution is in the form of y m equal to E m is a constant e to the power lambda m into y, where lambda m is the characteristic parameter. Okay. So, substituting y m is equal to E m e to the power lambda m y in this equation, say here it is 4th derivative. So, naturally we will get lambda m to the power 4, okay, and other constant will appear as it is E m, and when you differentiate e to the power exponential function, again exponential function will appear. So, exponential function will be common to all the derivative terms, and here also, because y m y is equal to capital E to the power m into exponential to the power m pi a by y. Okay. So, after substituting this, that means after substituting the derivatives of this y m, the assumed y m, here we get a characteristic equation of this form, that is E m is there and this will also appear here. Now, you can see that E m should not be a 0 for non trivial solution, otherwise we will not get any meaningful result, or we cannot go forward for the solution of the problem, and e to the power lambda y 0 is also non-zero. So, this quantity inside the bracket, expression inside the bracket is 0. Now, you can see the expression inside the bracket is nothing but the lambda square m minus m square pi square divided by s square whole square. So, it can be written as this form. Okay. That means, when we expand this, you will get again lambda to the power 4 m minus 2 m square pi square by s square lambda square m plus m to the power 4 pi to the power 4 a to the power 4. Okay. Now, this function can be factorized as this, because it is a square. So, we have written like that. So, you will get the repeated root as per the theory of equations. So, we get lambda m equal to m pi by a, again m pi by a, repeated roots, minus m pi by a and minus m pi by a. So, after getting this, the roots of the characteristic equation is this, whatever inside the second bracket, this is the characteristic equation. So, we have solved this 4th order polynomial and we got this, the 4 roots, and then we can write the solution simply as this E m 1, E m 1 is a constant, E m 2, because of repeated roots, here we are assigning a function y e to the power m pi by a y plus E m 3 plus E m 4 y e to the power minus m pi a into y. You can see this is the repeated root m pi by a, and minus m pi by a is also another repeated root. So, because of these 2 repeated roots, we have written this solution like that. If the roots are not repeated, then individually this, say the exponential function will be associated with this each of these constant, and there will be no variable y. Okay. Now, we know that exponential function and hyperbolic form of it is very useful in mathematical physics or any problem in engineering. So, therefore, I want to express this exponential function in terms of hyperbolic function. Okay. Now, the hyperbolic function can be expressed in terms of exponential function. We know that e to the power a x plus e to the power minus a x by 2 equal to cos hyperbolic a x, okay. That is known to us. Similarly, e to the power a x minus e to the power minus a x divided by 2 equal to sin hyperbolic a x. So, this is also known to us. So, you can see now, if I add these two, I can get e to the power a x. So, adding these two, say e to the power a x plus e to the power minus a x equal to 2 cos hyperbolic a x, and here e to the power a x minus e to the power minus a x equal to 2 sin hyperbolic a x. Now, when these two are added, we get we get e to the power x a x, and when these two are subtracted, when one is subtracted from another, we get e to the power minus a x. So, e to the power a x, you can see cos hyperbolic a x plus sin hyperbolic a x, and e to the power minus a x cos hyperbolic a x minus sin hyperbolic a x. So, our intention is to express the solution in terms of hyperbolic function. Okay. So, using the hyperbolic function with a x, suppose here we are having m pi a by y, is it not? So, let us substitute a x by m pi a by y, then we can write this equation in terms of hyperbolic function, replacing a x by m pi a by y, and then arranging the constant terms, because you will get cos hyperbolic, sin hyperbolic common with associated with other constant, then we can plug these terms and constant can be renamed, okay, as other constants. So, here the constants are renamed as am, bm, cm, dm, etc., and you will find that the solution can be written in this form: am plus bm y cos hyperbolic m pi a by y plus cm plus dm y sin hyperbolic m pi a by y. So, this is what is a homogeneous solution, but because the differential equation itself is a non homogeneous equation, you must find the particular integral also. That means, the solution for the loading function, if loading function is non-zero, okay, then you have to again obtain the solution of that differential equation, then you can superimpose these two solutions to get the complete solution. Okay. So, this is our solution 11(1) for this rectangular plate, which has two opposite edges. What are the two opposite edges simply supported? X is equal to 0 and x is equal to a. These two edges are considered to be simply supported. Other two edges at y is equal to 0 and y is equal to b, the boundary conditions are not specified till now. Okay. Let us see what we can do with this solution. So, we can write the total solution as y m y sin m pi x this. Now, you can see the earlier this solution is homogeneous solution. Here I have added another term, say pi. Pi is the particular integral or particular solution due to forcing function. If there is a no forcing load, for example, a plate is subjected to edge moment, then there will be no force, though in that case pi will not appear, but since the force is existing, so therefore, I have taken pi also along with this solution. So, total y m y is this function inside the third bracket, and it is multiplied by the function sin m pi x by a, which represents the waves in the x direction, half waves in the x direction in the deflected series. Okay. Now, sine function is used in the deflection series because it is obvious that two opposite edges are simply supported. So, only sine function is the appropriate algebraic or trigonometric function that can satisfy both geometric as well as force boundary condition. Okay. Now, what will happen if suppose here the y is equal to 0 and y is equal to b, these edge are simply supported. Okay. So, it is the y axis and it is the x axis. So, x axis is taken here vertical and y axis is horizontal, only to see what will be the difference with the expression that we have earlier obtained. Okay. So, one should not confuse that only x is equal to 0, x is equal to a should be simply supported. It is not like that. Y is equal to 0, y is equal to b, that the other two opposite edges y we did not touch here till now, that may be also simply supported. So, if this edge is simply supported, that is y is equal to 0, y is equal to 0 edge, okay, and y is equal to b edge. So, these two edges are simply supported, then we can write the solution just by reversing the function. So, earlier it was capital Y m x, now here it is written as x with index n as a function of x and sin n pi y by b. Okay. So, this is the difference in series, because it will be expanded with function of x and function of y is now a sine function, because the deflection and moment are 0 along the y direction. Okay. So, that is why we have taken this sin n pi y by b. B is the here represents the length of the plate, okay, in the y direction. So, by substituting in plate equation again similarly and making use of orthogonality condition as we have done earlier, we now arrive at this equation. So, that is nothing but del 4 x n dx 4. Now, here all derivatives of the functions are with respect to x. Previously, we have obtained the function with respect to y, because this function was assumed as a function of y. Now, similarly, we will get the forcing integral, that is the forcing part is a function of x, because when we multiply this by sin n pi y by b, this is the function and it is integrated with respect to y. The variable y will be replaced, has to be replaced by constant, which are the limits of the integral. So, therefore, the result will be a function of x. Hence, this is the differential equation right hand side, this non-zero part is a function of x. Okay. So, therefore, homogeneous solution becomes this. So, these are the constant again, but with the variable n. Okay. The harmonic number is here n instead of m. The general solution now can be written as a n b n x, a n plus b n x cos hyperbolic n pi b by x plus c n plus d n x sin hyperbolic n pi by b x plus particular integral into sin n pi y by b. So, that we have seen previously it was a function of y completely. The expression inside the second bracket was function of y, because the x is equal to 0, x is equal to a were simply supported. But in that case y is equal to 0 and y is equal to b are simply supported. So, therefore, the simply supported s function is satisfied by this sine function and other function must be a function of x, okay, in which pi stands for particular solution. Okay. Now, let me show you the characteristics of hyperbolic function, how it looks. You can see the cos hyperbolic m pi y or cos hyperbolic n pi x by a b, whatever we encounter in the solution, total solution in the complete solution of the Levis method, there we have to deal with this function that you have seen cos hyperbolic n pi b by x, or you have seen that it is cos hyperbolic m pi x by a, whatever may be. So, here you can see that if I plot this graph with m pi y by a with this index, then you can see the cos hyperbolic is a symmetric function. It is symmetrical with respect to your x and y axis. But if we plot say sin hyperbolic m pi y by a, we will see that it is antisymmetric function. So, that is the difference. Here cos hyperbolic is a symmetric function and sin hyperbolic is an antisymmetric function. Tan hyperbolic a x is nothing but just like your trigonometric quantity, it is sin hyperbolic a x, cos hyperbolic a x. Okay. So, we will be requiring to use several times this integration of sine hyperbolic, cos hyperbolic or derivative of sine hyperbolic, cos hyperbolic. So, you must be familiar with that. So, integration of sine hyperbolic is cos hyperbolic a x, cos hyperbolic a x, the integration is sine hyperbolic a x. Integral of tan hyperbolic a x is found out like that, okay. Because tan hyperbolic first I expressed in terms of the ratio of sine hyperbolic a x to the cos hyperbolic a x. Then after method of substitution I obtain the integral, okay. So, derivatives are also important. So, derivative of cos hyperbolic is sine hyperbolic a x, derivative of sine hyperbolic a x is cos hyperbolic a x, tan hyperbolic a x is like that. Now, the characteristics of the function is cos hyperbolic function is symmetric function and sine hyperbolic function is antisymmetric function. So, that statement is very important to solve the problems using the Levy's method, because in symmetric function if the loading is symmetrical or deflection boundary condition is symmetrical, then there will be no question of any antisymmetrical term in the deflection expression. So, naturally we can omit from physical reasoning. Then also we know the product of two symmetric function is symmetric, that is also true. Then product of one symmetric function and one antisymmetric function is again antisymmetric. So, suppose the x square is a symmetric function, okay, and sin x is antisymmetric function naturally. So, x square sin x is again antisymmetric function. Similarly, here say we have got, when we found the solution, we have seen that the terms y into cos hyperbolic m pi y by a appears. So, in that case y into cos hyperbolic m pi y by a, what will be the nature of the function? It will be antisymmetric, because y is antisymmetric function and cos hyperbolic m pi y by a is symmetric. So, product of one symmetric and one antisymmetric function is again antisymmetric. But when we see that y is multiplied by sine hyperbolic m pi y by a, then y is antisymmetric, sine hyperbolic m pi y by a is antisymmetric. So, product of two antisymmetric function is again symmetric function. So, that we will use. Then useful identity for simplifying the condition or solution, that cos hyperbolic a x square minus sine hyperbolic a x square is equal to 1. So, there is a difference that you can note in trigonometrical function, say if theta is the angle, cos square theta plus sine square theta is equal to 1, but here you can see cos hyperbolic square a x minus sine hyperbolic square a x is equal to 1. So, that identity can be used in simplifying the solution. Okay. So, integral of this tan hyperbolic a x is given here. Then we can see what happens when there is a symmetric loading and antisymmetric and symmetric support condition. Now, in many cases we adopt the symmetric type of construction, because symmetric structure or symmetric element is easy to construct, and also the load resisting easy to analyze also, and load resistance response to load is also favorable, because when there is a antisymmetric condition where there is a eccentric loading or anything, then in addition to your this vertical deflection, the twisting moment will be also of significant amount. So, therefore, in practical condition we will try to keep the structure symmetric as far as possible. Now, we call the structure symmetric when the loading and support conditions are completely symmetric. Now, here see this plate, okay. This plate has length a and width b, and two opposite edges are simply supported, x is equal to 0 and x is equal to a are simply supported if this represents the x axis along the length direction, and along the width direction the y axis is shown. Okay. It is not shown in the diagram, but consider that along the edge parallel to y, here the y axis parallel to width, the y axis exists. So, the plate here is symmetrical if I take the x axis or origin at the center of the left hand edge, then and we draw a horizontal line, then we can see that plate is symmetrical about that line, provided the other two opposite edges have also same boundary conditions. So, for example, the boundary condition may be simply supported on two opposite edges, or it may have this fixed clamped condition on two opposite edges, or it may have free condition at two opposite edges. For example, a slab culvert, you have seen the slab culvert, okay, or slab bridge. Slab bridge is also there for small span, only the slab is resting on the abutment. So, in that case you can see that if this line, these are the abutment support. So, it is supporting the slab on the two opposite edges just like a simply support, and the other two edges are free if there is no stiffening beam or girder. So, then these two edges are free. So, this condition may also represent a slab bridge supported by abutment at the two ends. Okay. So, in this case at x is equal to 0 and x is equal to a simply supported for other two edges being symmetric. Okay. Symmetric means condition we have not specified yet. Okay. Let us take x axis through the middle of the vertical side as shown in figure. Okay. Then the plate is symmetric, and we have seen the solution of this WXY homogeneous solution. Here you can see that when this cos hyperbolic m pi by a into y is multiplied by a m, then cos m pi a by y is a symmetric term, and sin h m pi a by y is antisymmetric term. But when the antisymmetric term is multiplied by another antisymmetric term, it will be a symmetric term. So, when the support condition and the loadings are symmetrical, then we can take the symmetrical boundary conditions, and therefore, the equation becomes simplified. That means, keeping only the symmetric term of the solution cos hyperbolic and y sin hyperbolic, because sin hyperbolic is antisymmetric and y is antisymmetric. So, product of two antisymmetric term is symmetric term. So, therefore, for this type of condition we have kept only symmetric terms. Okay. But when antisymmetric condition exists, then we will keep a m b m sin hyperbolic m pi y by a plus other terms say c m y cos hyperbolic m pi y by a, because in that case y is antisymmetric and cos hyperbolic is also symmetric. So, product of antisymmetric and symmetric function is again antisymmetric. So, accordingly, after knowing the nature of the function, now you have completely known, because graphical representation also I have shown. So, you can take appropriately the symmetric terms or antisymmetric terms. Okay. Now, different boundary conditions for this condition, say two edges are simply supported. So, if I take the x axis here running through the middle of the edges, vertical edges, then at y is equal to plus minus b, suppose this is the positive direction of x axis. So, it is y is equal to plus b by 2, and here it will be y is equal to minus b by 2. That simply supported boundary condition again have to be satisfied. So, these conditions are m y is equal to 0 and this condition m y is equal to 0, that means del square w del y square is 0, that means d square y m dy square equal to 0. Free condition, for example, y is equal to at b plus minus b by 2. So, for example, this is a slab bridge or a slab culvert. So, these two edges are free. So, in that case the condition here, the bending moment is 0. So, this curvature term is 0 and S shear is 0. So, S shear quantity is this quantity, and when it is differentiated with respect to this function, then m square pi square by S square comes because of double differentiation of this w with respect to x, because w contains sin m pi x by a also. So, this is the two boundary condition at the free edges. So, naturally imposing two boundary conditions at the two edges, okay, we will get the two equations, and that can be solved for two unknowns constants associated with the homogeneous solution. Okay. Then at the claim condition we have w is equal to 0 and the slope is 0, which requires that derivative of y m with respect to y equal to 0, because these edges along the y, the edges is clamped. So, the slope is 0 along the y direction. Okay. Now, examples of unsymmetrical edges. So, unsymmetrical edges, again we know that these boundary conditions will be different. Say boundary conditions, say if it is unsymmetrical, say this figure, we have shown this figure, this shows that y is equal to 0, edge is fixed, and y is equal to b, edge is free. So, because of this boundary condition, the plate is unsymmetrical plate. So, in that case the requirement is that at y is equal to 0, that means here along this edge the slope is 0 and deflection is 0. So, y is 0 and y m 0, that means y m, capital Y m is 0, and slope, that is that first derivative of y m is also 0. At y is equal to b, that is this edge, m y equal to 0, that is del square y m dy square equal to 0, and s shear 0. S shear 0 means third derivative of w with respect to y plus 2 into minus mu, mu is the Poisson ratio, plus del cube w by del y del x square equal to 0. So, this obviously reduces to this equation, and imposing this we can find the constants of integration. So, in that case the full equation have to be retained, that means we cannot omit any terms. So, 4 constants are retained here, and therefore, two conditions at each edge need to be imposed to find out these 4 constants of integration from 4 algebraic equation. After applying the boundary condition, the problem will be your this boundary value problem. So, you can calculate the constants of integration. Okay. Now, let us illustrate the Leibniz method in a rectangular plate which has simply supported edges, in the two opposite edges simply supported, but there is no restriction that Navier's method can only be used for all edges simply supported. Leibniz method is more general, that means when all 4 edges are simply supported, you can also use the Leibniz method, but Leibniz method relaxes more boundary condition, that means it is also applicable when other 2 edges are also differently supported. But one necessary essential thing is that 2 opposite edges must be simply supported. Now, here in this plate problem that I have taken here for this class, the x is equal to 0 and x is equal to a are simply supported this edge, and y is equal to 0 and y is equal to b also I have taken simply supported, and I have taken the axis y x axis running through the middle of the vertical edges. So, plate is symmetrical about this x axis, and therefore, symmetrical condition exists, and we can take now only this a m cos hyperbolic m pi y a plus d m y sin hyperbolic m pi y by a plus particular integral, because the plate is acted upon by uniformly distributed load of intensity q naught per unit area. So, the load generally expressed in the plate are per unit area when it is distributed. So, q naught is expressed as load per unit area, and because of the loading the particular integral is non-zero, and we have to consider this particular integral in this expression. All right. Now, let W be the particular solution for the case of uniformly distributed load. Now, here there are different ways of solving the non-homogeneous differential equation. One very attractive method for our physical problem, that is the problem encountered in structural mechanics, is the method of undetermined coefficient. So, in this method observing the nature of the forcing function or this non-homogeneous part, we can assume the possible solution. For example, if the forcing term is a constant, then obviously the solution is particular solution is also constant. If the forcing function is harmonic, say sine function, the particular solution should also contain functions of sine and cosine, that is harmonic. It may be cos also, it may be sine also. So, there may be a phase difference of course. So, a harmonic forcing function may require or may necessitate the particular solution as also harmonic. So, here seeing the nature of this particular integral, this forcing function as q naught, we first evaluate f m y, and f m y is evaluated by this integral that I have shown in the beginning, and that it becomes this value after integrating sine with respect to cos and then putting the limit, we get this 4 q naught divided by pi d m, where d is the flexural rigidity of the plate and m is the integer. And you can see that integral is valid only for the odd number of m. For even number of m, this function will disappear. So, you can see that when this m is equal to 2 or 4, 6 etcetera, then this function will be 0. The integration after putting the limit, it will give you 0 result. So, only the result that is obvious, it is minus 2 when m is odd number, that is 1, 3, 5 etcetera. Okay. So, we get this f m y as this function, and this is obviously a constant. So, therefore, we assume that particular integral or particular solution is also a constant. So, let us assume that W p equal to c, where c is a constant. Substituting these 3 in equation 1 is this. That means, if this is a solution, then it must satisfy the differential equation, that is the philosophy. So, after substituting this, we get when the constant is substituted, y m is equal to constant, then this term goes to 0, this also goes to 0. So, here it will be m to the power 4 pi to the power 4 divided by a to the power 4 into c equal to the constant. The constant is 4 q naught pi d m. So, after doing this, we get this equation from where c is obtained as, c is nothing but particular integral is 4 q naught a to the power 4 m to the power divided by m to the power 5 pi to the power 5 into d, where pi is the your this m appears with a fifth power, you can see. So, it will be rapidly converging. So, m contains the power of 5. So, when this first term is taken for deflection, you will get almost accurate result. When the second term, that is 3 is taken, 3 to the power 5 in the denominator will decrease the value drastically. So, the series will rapidly convergent after taking a certain terms. Hence, the complete solution is for y m is y m y equal to a m cos hyperbolic m pi y by a plus d m y sin hyperbolic m pi y by a plus 4 q naught a to the power 4 m to the power 5 pi to the power 5 d. D is the flexural rigidity. So, now let us see how we can impose the boundary condition. So, refer the figure of the question that the simply supported plate here again, and this is the x axis and this is the loading that applied on the plate. Since at y is equal to plus minus b by 2, when y is equal to plus b by 2, that means this edge, or minus b by 2 is this edge, then the boundary condition is same. So, first applying the boundary condition on this edge y is equal to b by 2 on deflection. Okay. So, deflection series, that means this expression will come, and when you substitute y is equal to b by 2, this function will be 0 of course, because at y is equal to b by 2 your deflection is 0. So, y m is 0. So, a m cos hyperbolic m pi b by 2 a plus d m b by 2 sin hyperbolic m pi b by 2 a plus this term due to particular solution 4 q naught a to the power 4 divided by m to the power 5 pi to the power 5 by into d. Okay. So, this term is written and this constant term is transferred on the right hand side with q naught. Okay. Then from other boundary condition, that is the second derivative of this y is 0. So, first derivative is taken, very carefully you have to take the derivative, otherwise there is a chance of committing mistake in the solution. So, first derivative is taken, then second derivative is again taken of this function, and you can see now the imposing the boundary condition at y is equal to plus b by 2 or minus b by 2, that curvature in the y direction is 0, because the edge y is equal to 0, y is equal to b is also taken as simply supported. That means, here not y is equal to 0, y is equal to b, because the axis is taken running through the middle of the vertical sides. So, that means, y is equal to plus b by 2 or minus b by 2, the edge is simply supported. So, substituting this the boundary condition on second derivative, we get this. Now, you can see that two unknown constants and two equations are obtained. Okay. One condition is obtained using the deflection condition, okay. That is the equation. Second equation is obtained by imposing the curvature condition, that is bending moment equated to 0. So, these two equations are of the form, say C 1 A m plus C 2 d m equal to Q 1 plus, this is one equation, and another equation is C 3 A m plus C 4 d m equal to 0. So, because of the loading, we get this as non-zero term Q 1. Okay. So, two equations are obtained and two unknown, and these are algebraic equation, and this can be very easily solved, where the C 1 are the coefficient that can be collected from this expression, and you can see that this is the second equation for this imposing, after imposing the boundary condition on bending moment. So, therefore, C 1 we get this C 3 that we get is written here. C 3 is m square pi square by a square cos hyperbolic m pi by b 2 a, and C 4 is this quantity that is written here. Q 1 is the right hand side of the first equation, this is. Okay. So, these two algebraic equations are written in equation number 8, and coefficients are identified clearly. So, this can be solved by using any rule. Okay. The easiest rule is Cramer's rule, using the determinant. It is a systematic procedure, and you can find that using Cramer's rule, the coefficient, the variable a m, the unknown constant a m becomes this determinant of Q 1 C 2. I am telling you row wise. So, Q 1 C 2 0 C 4 divided by delta. What is delta? Delta is the determinant formed by the coefficients associated with the a m, b m, c m, a m and b m. Two variables are there. So, a m and d m. Okay. So, similarly, you have we get this, that the first coefficient is a m. So, first column is replaced by the right hand side value. So, right hand side value is Q 1 due to forcing term. In second equation it is 0, and the second column contains the coefficient C 2 and C 4. Similarly, for the second variable, that is d m, we get this second column as the forcing term Q 1 and 0, and the first column with the coefficient associated with a m C 1, and the second row coefficient associated with a m is C 3, and delta is the determinant that is formed by the coefficient, and it can be found out by expansion. So, after doing this algebra, we can get the value of a m as this quantity and value of d m as this quantity. So, once the value of a m and d m is found, then you can completely write the equation, okay, completely write the equation for y m y. So, y m y is written completely, because this is known and this is known, and these quantities are known. So, After writing this equation, we get now the complete expression for y function. Okay. It is given like that, and the deflection is now y into sin m pi x by a. Now, a rectangular plate carrying uniformly distributed load, and we see this symmetrical support condition simply supported along all edges. The standard result we know from Navier's solution already, and we can compare our result that we obtained by Levis condition. So, maximum deflection is obtained at the center of the plate, that is x is equal to a by 2 and y is equal to 0. Okay. Now, for example, the plate is a square plate, that is a is equal to b. Then after putting this a is equal to b in this expression of deflection, because now the quantities are completely known, and taking the summation with any number of terms. So, if we take first term, you will get the accurate result, enough accurate result for the deflection. Of course, for bending moment you require more terms to get the convergence of the series. For shear, still more terms. Okay. So, for deflection quantity, we take only first term, and taking first term and a equal to b, this series is evaluated because y m is completely known, m is taken here as 1, and whatever value here, that for y m is substituted as 1. So, after calculating this, the deflection is found to be 0.00406 q naught a to the power 4 by d. So, this quantity coincides with the value that we obtained earlier by Navier's method. Okay. So, Levis method has application in more general cases compared to your Navier's method, because Navier's method has severe limitations, because all the edges must be simply supported for a rectangular plate, otherwise double trigonometrical series cannot be used. But Levis method relaxes one restriction, that is two opposite edges only need to be simply supported, other two opposite edges may have any condition, may have same condition or may have different condition, does not matter, classical or non-classical boundary condition, anything can have, but requirement is that two opposite edges must be simply supported. Without that, Levis method cannot be used. So, let us see what we have done today. In this lecture, the analysis of rectangular plate whose two opposite edges are simply supported is discussed with an exact theory, because Levis method is an exact theory. It yields the closed form solution, closed form expression for the differential equation of the plate. The method is popularly known as Levis method. With the help of single trigonometric series, because the two boundary conditions are known only. So, one sin function is taken in the deflected surface assumption first. So, with the help of single trigonometric series, the general solution for any loading function is derived. We have derived this general solution for other function, that is y, for any loading condition. Particular integral of course have to be found out depending on the nature of the load. That I have told you that best method to apply in the plate problem is the method of undetermined coefficient in the theory of linear differential equation, non-homogeneous linear differential equation. So, general solution is derived by the principle of superposition, that means homogeneous solution is first obtained and particular integral is added to this to get the complete solution. But the constant of integration are evaluated imposing the boundary condition. In general, there are 4 constants of integration, and 4 constants of integration requires 2 boundary condition on each edges. So, that have to be applied, but this requires only if the conditions are completely unsymmetrical. But if this is antisymmetrical or symmetrical, we can use only the 2 constants appearing in the homogeneous solution of y, because other 2 constants can be dropped. If the conditions are symmetric, antisymmetric term in the deflection function can be dropped. Similarly, if the condition is antisymmetric, then this antisymmetric this symmetric function can be dropped. Anyway, the results are simplified based on the condition of symmetry. So, that we have utilized and we have compared the results of simply supported plate, means plate, rectangular plate simply supported along all edges, and this is analyzed for deflection using Levy's method, and we knew the results obtained from Navier's method, and it is also available in the textbook. So, we have seen that two results coincide and are in well agreement. So, Levy's method you have understood, it is more general compared to this Navier's method, and in our next few classes we shall explore this method to obtain the solution for other boundary condition and for other load conditions. Thank you very much.